This is our formal lab on Plato resistors. The main problem that this lab works to address is how we can model a Plato resistor and circuit so two electronic elements, a fan and an LED, operate concurrently. Our main punchline is that we use trial and error to develop a circuit that fits specific electrical criteria. We modeled a resistor with Plato of a specific resistivity to ensure all elements in said circuit operate at the same time. Our motivation for conducting this experiment is that knowing how to manipulate the properties of a resistor to fit specific criteria reveals the complex nature of circuit design and can be used in everyday applications. Our experimental findings are that organizing the elements of the circuit in a parallel configuration with the fan and standard resistor in series, as well as modeling a Plato resistor with a length of 5 centimeters, a cross-sectional area of 7.0 centimeters squared, and a resistivity of about 10 ohm meters, causes all the elements to operate concurrently. Here is an outline of our experimental procedure. We predicted the resistance of each circuit iteration, accounting for the Plato resistor for each one. For the construction of each circuit, we used three 5-volt batteries, a 2.7 ohm standard resistor, 10 alligator clips, a blue LED, a motor powder fan, and Plato. We developed three circuit iterations across the experiment to accommodate for specific criteria, which are the fan requires approximately 300 milliamps of current and the LED needs about 2 to 3 volts. We used solder leads to implement the Plato resistor into the circuit for all iterations. We used the pre-lab data to manipulate the dimensions of the Plato resistor to fine-tune the circuit and make sure the LED and fan work at the same time. We used the multimeter to measure the voltage, current, and resistance of all the elements in the circuit. Here's our experimental limitations. First, the Plato could have been too dry in some of the earlier circuits. This could cause the current to not flow properly and cause some elements of the circuit to work but not others. Additionally, if the batteries aren't fully charged, the voltage they deliver could be lower than 5 volts. This could affect the power of the circuit as a whole and could lead to inconsistencies between observed and calculated values. Also, if the multimeter wasn't properly calibrated, it could display incorrect values, which also causes inconsistencies. To minimize errors, we use water to dampen the Play-Doh. The water should increase the conductivity of the Play-Doh due to its polar nature. We also started every circuit iteration with the same dimension Play-Doh resistor for consistency.
So we went through three iterations of our circuit before we reached our eventual final one, was our fourth. So we tried out one battery. We had our Plato resistor in series with our LED. Both those were in parallel with our motor with a fan. That can be seen in our V1 circuit iteration here. From there, we figured, if this wasn't working, maybe we need more voltage. We're voltage limited here because we knew that the fan would work, but not the LED. So we tried adding in a second battery. That didn't work either. So we figured, maybe we're still voltage limited. We can still get one to work and not the other. We'll try adding in a third one. And based on the results of other groups who were successful, we figured, maybe we could try switching the Plato resistor from being in series with the LED and parallel with the motor to being having everything in parallel to try to, change things up so that everything would work at the same time. That unfortunately did not work either. So that brought us to our final iteration of the circuit, which you can see a picture of the actual circuit on the left here, and we have a diagram of the circuit on the right. So essentially what we did is just we took our V3 circuit from before and we added in a 2.7 ohm resistor in front of the motor, and that allowed us to get the current necessary to run the motor, and it did not pull enough voltage towards that side of the circuit so enough could flow through the LED and that would still work, which is exactly what we were going for, and you can see that in the picture here. Now, once we got this, everything working, everything set up, we took some measurements off of our circuit. So we had our three batteries giving off 3.14 volts and 3.5 amps. You can see that there was, this wasn't a perfect circuit. There was some voltage and current lost. But for our Plato resistor, it had a voltage drop of 3.05 volts and a current of 2.4 milliamps across it. For our LED, it had a voltage of 3.05 volts and it had a current of 19.7 milliamps. And finally, for that last kind of little bit in series, that last parallel section, our resistor had 1.97 volts across it and 0.66 amps, and our motor had 0.86 volts and 0.66 amps across it.
All right, so to analyze our circuit, we must use Kirchhoff's laws of current, which means that the current flowing into a point must equal the current flowing out of a point. And Kirchhoff's laws of voltage, which means that the voltage drop across closed circuit must equal 0. Additionally, we will use Ohm's law, and we will use the equations for calculating resistivity of parallel resistors and the resistivity of resistors in series, shown here. Once we plug the numbers in, calculating for the resistors in series as well as all of them in parallel, we find that the total resistance is 0.24 ohms.